We're very happy to welcome Anna Rosen to Carnegie virtually today for the colloquium. So Anna finished her PhD in 2017 at UC Santa Cruz, and then she's been at Harvard since then. So first as a Einstein Fellow, and then currently as an ITC Fellow. Anna's an expert in various aspects of star formation, and we're excited to hear everything she has to say today. So if you have questions, go ahead and just use the raise hand feature. And then Anna, if you see people with their hands raised, feel free to answer their questions directly, or I can also interrupt you in case.
Yeah, feel free to interrupt me. I don't actually.
Yeah, I'll keep an eye on the people's questions and stuff.
Yeah.
I'll interrupt you.
I don't see how.
Sounds good. All right, so go ahead and take it away, Anna.
Great. Well, yeah, thank you so much. I will admit I'm kind of bummed not being out there. I'm actually from the San Fernando Valley, so looking forward to visiting Carnegie, but luckily I have collaborators there, so we'll definitely try to visit in the future. But yes, so thank you for the invitation. Today I'm going to talk about some of the work that I've been doing with others about massive star formation, also looking into feedback in massive star clusters and how that affects the formation of star clusters. So just to kind of begin, let's talk about like what is stellar feedback. And this is like a great example showing how impactful stellar feedback is on the star formation process. So stellar feedback is just the injection of energy and momentum by young stars into the interstellar medium. And if we look here, this is 30 Doradus in the LMC. It is basically the biggest H2 region in our local universe. It has what are known as superstar clusters. So these are very dense star clusters with a lot of massive stars. And this is a beautiful composite image showing how feedback from the different physical processes actually affects the gas distribution within these clouds. So as you can see here, there's this very dense star cluster. This is R136. It's about a 1 mega year old. It has some of the most massive stars that we have observed. Some stars, maybe as massive as 200 solar masses. And now with these multi-wavelength observations, we can see the different impact that these stellar feedback processes have. And so this comes in the form of radiation pressure. So this is radiation from the stars themselves, dominated by the massive stars because they're very bright. And so if you look at the cool gas, or the yellow here, that's showing that the H alpha, which is basically the cool gas that's illuminated by the stars, and this gas is dusty, and so the dust is going to absorb radiation from that's emitted by these stars, and that's going to heat up the radiation, the dust, and then that dust will thermally re-emit. And so you get this in the red. From the infrared, you can see this added addition of what's known as dust for process radiation pressure. So radiation feedback has a large effect. Likewise, because the massive stars are so bright, they give off these really strong stellar winds, and these winds are very fast, leaving the stars greater than 1,000, the star's surface greater than 1,000 kilometers per second, and the collision of these winds with the surrounding ISM and nearby winds will actually generate this really hot, low density gas, this shock heated gas, that then the hot gas pressure causes it to expand and carves these holes in this giant H2 region. You can see that with the X-rays here. So effectively, stellar feedback, basically if gravity was acting alone, you would expect all this gas would be converted to stars. But because stellar feedback injects so much of this energy and momentum and impacts the surrounding environment, it actually reduces the star formation rate in molecular clouds and can have a damaging effect. And stellar feedback in star clusters, at least star clusters that are forming massive stars, will be dominated by the massive stars themselves. But the question too is, well, we know that massive stars are very rare, so why are they so important? If you look at, let's say, for example, Krupa IMF, so the initial mass function, which just talks about the fraction of stars for a given mass in let's say, a newborn stellar population, you find that only about 1% of stars are massive. But if you actually look at the radiation output, because these stars are very bright, basically the most massive stars are about, 1 million times brighter than our sun. What you'd find out for something like for R136 and 30 Doradus is that about 97% of the radiation energy that we see is actually from the massive stars. And so I like to think that massive stars are the 1% of the universe. So they're very destructive and have a huge impact. And like I mentioned before, they influence their environment in a variety of ways. The first is radiation pressure. So this is radiation on dust grains, but also the photoionization. So since these stars are so bright, they give off a lot of high frequency radiation that is absorbed by neutral hydrogen and photoionizes it. Likewise, you have the stellar winds, which are just as important. These are radiatively driven winds that are launched from the surface at fast speeds. And then also during their formation, you have protostellar outflows. So these are collimated jets that are ejected as the stars are actively accreting. And then finally, at the end of their lives, you have supernovae explosions. And so I'm going to focus on the first of these three processes, since I'm going to focus on the formation of massive stars. And the idea is that basically that stellar feedback may eventually halt accretion into stars, and thereby, setting the upper mass limit of the initial mass function. But then on medium scales, like I showed before with 30 Doradus, stellar feedback reduces the star formation rate and star formation efficiency in molecular clouds. And so just a small fraction of the gas is actually converted into stars. And if feedback is efficient enough, you can actually eject a lot of the gas. And this is a lot of work that Mike Rudick and David Gushinov has been looking at. And so you can actually, within stellar clusters or in GMCs, stellar feedback can actually shut off star formation. And so this is very important because then, of course, the gas that's ejected can be ejected from galaxies, and this could lead to galactic winds. And so throughout the whole galaxy, stellar feedback leads to inefficient star formation and then potentially can eject a lot of the cool gas. And so this is very important in the context for studying galaxy formation and evolution. And again, if we look at a composite image, different wavelengths, we see that, for example, looking at Spitzer, Hubble, and Chandra, where you have these big outflows from the galaxy where the star formation is likely highest, or a lot of supernovae going off. And you see that this hot gas generated by stellar wind and supernovae feedback is actually launching a lot of the cool, dusty gas out of the galaxy that would have otherwise formed stars. So even on the small size scales of massive stars, it has a huge impact throughout the whole galaxy. So hopefully I convinced you that stellar feedback is important. Luckily, people writing papers also find that it's very important. I realize that I have not updated my 2020 numbers, so this is probably much higher. But this is just looking at all the articles since 1990 that has the term stellar feedback in the abstract. And so this is neglecting individual components. And so this is a self-selection anyway, so these numbers are probably much higher. So stellar feedback is a very important concept that we're all studying now in many different areas of astrophysics. But the main point I want to give home is that when we talk about stellar feedback, we're really talking about stellar feedback from the massive stars, because those will have the biggest influence in the galaxies in which they form. So the first question is, what are the initial conditions for massive star formation? So there's two competing theories. There's what's known as core accretion, and this is similar to low mass star formation, in which you have a core material, so a dense core material that will undergo collapse, and that acts as the whole mass reservoir for the star. So a lot of theoretical work and now observational work trying to find these cores have found that if you have a large enough core and it's supported by, let's say, turbulence or magnetic fields, then you can actually have large enough accretion rates. So virialized cores, this would have large enough accretion rates to actually to form massive stars, or 10 to the minus 4, 10 to the minus 3 solar masses per year. One of the problems with this theory is that you have to have the existence of these very dense cores and have them be supported by turbulence or B fields. And so, a lot of observations of massive star forming regions have been looking for these massive prestellar cores, and they find that they typically tend to be subvirial. So you can, if the magnetic pressure in these cores is strong enough, you can actually have virialized cores, but that is still a work in progress. Another idea is what's known as competitive accretion. And this kind of suggests that masses, like the subsonic cores that low mass stars form out of, can act as the seeds of massive stars, but they end up in the basically the gravitational potential. And so basically the mass flow within the molecular clouds will deliver material to a few select sites that are at the bottom of the gravitational potential. Some of the problems with this too is that you have to have Jeans mass fragmentation. What we're seeing now is a bit more complicated with that. Also not all observed mass of course fragment on the Jean scale, but this also depends on the influence of magnetic fields and so on. And that is still a work in progress because measuring the strengths of magnetic fields is still very tricky. Furthermore, we are seeing a lot of dynamical accretion in these environments. Like this here is STC 13, and you can see you do get these large accretion flows at the locations that these dense hubs or massive stars are forming. So with that being said, Mike is doing a lot of really nice work on this with Starforge, with the Starforge simulations. So I highly recommend chatting to him for more detail because he's looking at where all stars come from, basically. Likewise, going back to this dynamical picture of star formation, here's an example of SDC 335. There's two very massive stars with powering these large molecular outflows. And what Adam Abelson finds is that you do get these large filamentary inflows of material that are feeding these stars, and the accretion rate onto these stars, and the accretion rate onto this clump is about 0.5 parsecs in radius, is about the same. So basically the mass flow from large scales is in agreement with the mass flows into the stars themselves.
I didn't get that. Could you?
Sorry, that was my Apple Watch. So basically massive star formation is a complicated picture. Like I said, definitely talk with Mike because he's doing a lot of nice work with this. It's a multi-scale, multi-physics problem that relies on several different physical processes. But my work that I'm going to mostly focus on today is a more simplified picture of how do when you have let's say a massive prestellar core and you include feedback, different forms of stellar feedback, how does that actually affect the formation of massive stars? And so first I'll talk about radiation pressure. So this was one of the first feedback components studied in the context of massive star formation. And that's because there's a simple model, like 1D model, where if you assume an isotropic accretion flow, it leads to this, what's known as the radiation pressure barrier. So you're basically equating the gravitational force with the radiative force. As the star grows more and more in mass, it gets brighter and brighter. And so eventually you can reach a point where the radiative force is greater than the infall due to gravity, and then that will overturn the accretion flow. And that of course depends on the light to mass ratio of the star, and also this trapping factor. So this one here corresponds to the direct stellar radiation pressure. But then, like I mentioned before, the primary absorber of the radiation is by dust that will reheat in agreement. So you get this added component, and that's parameterized by this trapping factor. And so when this was first studied way back in the 70s, people didn't think that you can get stars greater than 20 solar masses. However, we knew that, or not me, I wasn't alive, but people knew that stars greater than that, existed. Not only that, we're finding now that stars as big as 200 solar masses might exist. So, for example, looking back at 30 Doradus, which is one of our most extreme star-forming environments, Schneider et al. Find that within R136 there could have been stars as big as 200 solar masses. So one question that we're all very interested in is actually, well, what sets the final stellar masses or the upper mass limit of the IMF? Is that due to stellar feedback? And so one way to look into this is to kind of do this piecewise analysis to see how the different feedback components actually affect star formation. So of course, we turn to numerical simulations because, like I mentioned before, massive stars are very rare. The sites in which they form are very dense and very hard to see through. And so we can basically get a nice picture of the formation by turning to numerical simulations. So modeling radiation pressure and star formation is, as I mentioned before, is extremely important. It's also extremely hard. So when I was a grad student, I developed this hybrid radiated transfer method that modeled both the direct radiation pressure So we use adaptive ray tracing for the stars themselves, and then we use a moment method. So this is approximation to the radiative transfer equation in numerical simulations for the Desper process. So this is like a gray, single frequency. And then the hybrid part is that we combine them together. So you solve for the direct radiation, you adjust the, you add the energy and momentum into the dusty fluid, and then you treat the radiation pressure from the fluid itself. Since we are using adaptive ray tracing, it's quite simple to have a multi-frequency approach, which is very important because if you look here, this is the frequency, this is the opacity on dust as a function of wavelength. And so you can vary by orders of magnitude. So in the context of massive star formation, where you're going to have a lot of high energy photons, you really want to be able to capture the frequency dependence accurately. This was added to the Orion AMR, so adaptive mesh refinement numerical simulation code. Simulation codes like this are really just solving the equations of conservation. So conservation of mass, momentum, energy, radiation energy. This is solved in the Cartesian grid. So to treat stars, we actually have Lagrangian sync particles, and these act like particles connected to the grid that can accrete nearby material, and also, eject material and eject energy and momentum into the gas. And then you solve the Poisson equation to be able to update gravity. So this is an example of my PhD work showing how radiation pressure actually affects the formation of massive stars. So these are two different views. So this is the whole core. The bottom panel is a zoom in of the core, looking at two different directions. So we see the core is supersonic turbulence, this is a very dense core, and then we just let the gas do its thing, and you can see that you get these dense filaments feeding material to the star. Once the star becomes sufficiently massive, the material starts to be blown away by radiation pressure, and these bubbles grow with time. But one thing you see too is you get this dense material along circumstellar material surrounding this along the equator of the star, and that's just an accretion disk. So really, you're still supplying material to the star, it's actively accreting, but radiation pressure is blowing material away. And what that means is that you get what's known as this flashlight effect. You can see that here. So you blow these radiation pressure driven bubbles, you develop an accretion disk that grows with time because you're now accreting material from farther away with higher angular momentum. And then eventually those bubbles will start to expand. But what we find is they actually become Rayleigh-Taylor unstable. And so that just means because you have these low density bubbles, so this is just a thin density projection showing these processes, you see that these bubbles expand far away, but they eventually become unstable because you have a thick or a dense shell surrounded by a low density bubble of material that's expanding due to radiation pressure. And the main thing is that you overcome the radiation pressure barrier if the ram pressure, the infalling material, is large enough. So here, for example, this PRAM, this is the spherically average. So you see, we would expect if you just did the simple isotropic approach, the radiation pressure should be overcome the infall of material when the star reaches 30 solar masses. But when we look at the material that's actually falling in, so taken to the anisotropy of the infall of material, that basically the ram pressure is large enough to overcome that. And at the end, we get this one-to-one relationship. And so our main results in agreement with previous work is that you just really need an anisotropic accretion flow to overcome the radiation pressure barrier. Likewise, I've also looked at how does the virial state of the core affects the accretion rate and fragmentation of the core. And so this is two examples, so similar simulations, excuse me, except now we have a core. So this is the core that I just showed you. It was a sub-virialized core versus a virialized core, so a higher velocity dispersion. And we find that affects the accretion rate. So the subvirial core, you get this instant collapse because you're not supported against gravitational collapse, so you grow a lot faster. But then eventually, once you're dominated by the accretion disk, the inflow material is dominated by the accretion disk, it's roughly similar. Likewise, because when you have a higher velocity dispersion, that you develop more shocks, that can lead to denser material that forms, that becomes genes unstable. You end up undergoing a larger scale of turbulent fragmentation. So in this case, with a subaerial core, we have no turbulent fragmentation, but we do get some disk fragmentation at the end. Whereas if you have a higher velocity dispersion, that leads to more overdensities within the core due to the shocks colliding due to turbulence. You undergo this period of turbulent fragmentation that subsides, and then eventually you build a large enough accretion disk around the star that then undergoes gravitational instability and fragments to form companion stars. Okay, so then what about protostellar outflows? And how do they work together with radiation pressure? Well, we know that protostellar outflows are ubiquitous in star formation for both low mass and high mass stars. And this is just due to the fact that, like I showed before, you get this accretion disk. We know that massive star forming regions are magnetized. And so you basically will drive these magnetically launched collimated outflows or jets near the star. And then as those jets are ejected away from the star, they will entrain molecular material and eventually launch material from the core, as shown in this nice picture by Charlie Latta. Likewise, the outflow force that are measured in these, the outflow force that's measured in these entrained outflows that are commonly observed, usually by CO emission. The momentum in the outflows is larger than the momentum in the radiation field. So actually the momentum delivered by outflows is more powerful than the momentum delivered by stellar radiation, even though the energy delivered by radiation is a lot higher. So you would expect that basically these powerful jets will actually drive these wide angular molecular outflows and eject core material. And this should be important because you get this efficient ejection to actually set the star formation efficiencies of massive prestellar cores. So in a similar fashion, this is showing a couple of different snapshots where we look at radiation only. So this is starting with the virialized core. Then we include outflows, and you can see that obviously when you don't have these outflows, because we eject, we say that a small fraction, about 20% of the accretion of material is actually being ejected. And so the stars themselves grow slower. However, within the same time, you get these powerful outflows that are ejected from the star. And these outflows basically allow a path for the radiation to vent out. So this is showing for the gas here as a function of stellar mass, that basically, the effective core temperature, so this is the mass weighted core temperature, is similar. But then once you get this breakout, which happens at about 20, 25 solar masses, you find that the temperature kind of cools in a way, and that's just because you're basically letting the radiative flux vent out. So in a way, the influence of outflows increases this flashlight effect, and it reduces the radiative heating of the core material. But what about magnetic fields? So the simulations I presented so far do not include magnetic fields. And the influence of magnetic fields should actually just slow down the collapse and reduce fragmentation of the core. Oh, and also too, so this is work from Crucio et al. Looking at the inferred magnetic field strength for a large number of molecular clouds and dense star forming regions. And he finds that in the densest gas that these molecular gas tends to be supercritical, meaning that gravity is slightly greater than that from the magnetic pressure. So you should still gravitationally collapse, but it'll just slow down. So we included that. We included the effect of magnetic fields too. So here I'm showing the results of 3 different simulations. When you have radiation only, so you don't have outflows, you do find a higher accretion rate because you're not losing material to the outflows themselves, as compared to when you do include the outflows. But then also when you include magnetic field, you get a weaker or slower growth rate of the massive star, because the magnetic field kind of acts like slows down the gravitational collapse of these cores. It opposes gravitational collapse. So you just end up with the lower mass loss, mass accretion rate throughout the formation of the star. One thing too with magnetic fields is that it also you have this effect of magnetic braking. So as material is falling down, you can have magnetic flux removing some of the angular momentum from the accretion flow or from the infalling material. And so that can reduce, the size of the accretion just that you expect. I should also warn that these simulations don't include non-ideal MHD effects such as ambipolar diffusion. Non-ideal MHD effects will likely reduce that angular momentum removal. And there's some previous work that's been put out that has shown that. But we do get, like I said, fragmentation is highly suppressed because you have this added pressure. Another thing too is, if we look at the bubbles, so the radiation pressure bubbles that form from the radiation pressure from the star, we see that if we just look at the radiation plus outflows, these get quite large. However, they're much smaller when you include magnetic fields. And so here is just a zoom in at this snapshot here, where we do get this nice small bubble, radiation pressure dominated bubble, and we see that it's a lot smaller due to magnetic tension. So as the radiation pressure is trying to cause these bubbles of hot, radiatively driven gas to expand, that's going to sweep up magnetic flux, increase the magnetic field in the shells. And as you can see, the direction of the magnetic field is basically perpendicular to the expansion, and that will kind of hold it together. So you get this magnetic tension that actually makes radiative feedback less effective. You can also look at the structure of the outflows, of the intrain outflows from both of these effects. And the first thing to notice too is the outflows are very messy. This is an agreement with lots of observations. So one of the biggest tracers for finding where massive stars are forming is to search for these intrain outflows. And so there's a lot of observational data on that. And so this is looking at, if we just for now neglecting magnetic fields, we find that you get these messy outflows, and that's just because as these stars are accreting material, they're being knocked around, so they're precessing, and that can lead to these messy outflows. But when the gas of the core is magnetized, you actually get these broader outflows. And I will admit, if you look at the messy CO emission maps from a large sample of outflows, this looks, pretty similar to that, which is nice. And the reason why you get these broader, lower density outflows is because you actually get this magnetic levitation effect. It's kind of because of the magnetic pressure, it's kind of easier to push to cause these outflows to expand. And so when the core is magnetized, you do find that the filling factor of these outflows is larger than you would expect if the core is not magnetized or has smaller magnetic fields. So because of this magnetic levitation effect, you get this larger collimation angle. And then finally, we can also look at the mass momentum and the energy budget of the mass that's injected by outflows, or the mass, the energetics that's injected by the outflows, and compare it to what's actually in the entrained outflows. So in agreement with our model, we find that about this 3-to-1 ratio, that the entrained mass is about a factor of 3 larger than what's actually launched in the outflows. Likewise, we see an increase too. So looking at the momentum of the entrained outflows divided by the injected momentum, and same for the kinetic energy, you find that about, you don't have this 1-to-1 relationship. So the amount of energy and momentum I'm putting in to the outflows is not going to 100% be seen in the entrained outflows. And that means that you're losing some of the momentum in the outflows anyways. And so we see that about 25% of the momentum is in these outflows, whereas in the entrained outflow is delivered to the entrained outflows, and you're likely losing energy due to expansion, radiative cooling, and so on. And then same with these entrained outflows, only about 5%. And so more work needs to be done with this, and we plan on looking at this with StarForge for a much larger number of stars to kind of see, what would be a good way to parameterize the momentum and energy injection for protocellular outflows and other forms of feedback, because what you put in is likely not what you get out. And that's very important for, let's say, cosmology and galaxy formation simulations, because you don't want to overestimate feedback and you don't want to underestimate it either. And then again, we can compare our results for the star formation efficiencies and the energy or the forces or momentum within these outflows. So we find that basically when you do not have outflows, the star formation efficiency you get at the end is too big. So here this 40% is from Mott et al. 2015. 33% is the canonical value that we expect for low mass star formation, looking at the core of this core mass function to the IMF and initial mass function. And so we see that you really require outflows and magnetic fields to agree better with what we're seeing. Like I said before, these do not include non-ideal MHD effects. So we would expect that if non-ideal processes are at work, that will make magnetic fields less effective. And so we'd likely have a higher core mass star formation efficiency here. And then if we look at the outflow force, so this is comparing to Mott et al. 2015, his next paper in this series. So this first paper was looking at the core formation efficiencies of these massive star forming regions. And then the second paper was looking at the energetics of the outflows, and we see very good agreement. So here the dotted line is what's extrapolated from low mass, the outflow force measured from low mass protostellar outflows. Whereas with Mott et al. 2015, this is the fit that they get for looking at massive outflows. And so we have very good agreement, which is always a plus when you're simulating something. Okay, now I'll just briefly talk a little bit about something that I'm writing up now, which is now including the impact of stellar winds on massive star formation. So this hasn't really been done before in the context of these core collapse simulations. And so like I mentioned before, stellar winds will be launched when the star is sufficiently hot, because these are radiatively driven winds. And you find that the interaction of these winds, as they leave the stellar surface, because they travel so fast, you're going to get this shock stellar wind material. And if you assume all this energy is thermalized, you should get gas, low density gas, that's millions of degrees Kelvin hot. And that's assuming all the kinetic energy injected by the winds is thermalized. And then because of the hot gas pressure, you get this adiabatic expansion that can be quite important. So this is similar to the same setup I showed before, but now we include the impact of stellar winds. And one thing I will note, because of course, with most simulations like this, especially since this is AMR, or on a Cartesian grid, is that we're limited by the Courant condition. And so that means you can't really have a time, you can't really, you can't really kind of solve this with large enough time steps, such that the information, basically, okay, the Courant condition is basically saying like, you can't advance information faster than it can travel. So this severely limits your time step. And so once we get this really hot gas and we have these really fast winds, the time step drops like crazy. So these simulations are lower resolution. So the simulations I've been showing so far, we have 20 AU resolution, the finest level, and these are 40 AU resolution per cell resolution. And that's just because once winds become important, the time steps I was finding able to drop by a factor of 10. However, we still get a lot of really interesting results. So this is showing, oh, sorry, I didn't put that on here, but each panel here is about 0.1 parsec in area, parsec squared in area. And I'm just doing a thin density projection with the massive star at the center. And we're basically the up axis here is just perpendicular is parallel to the angular momentum axis of the gas near the star. So this way we can see how, once we form an accretion disk, how that affects the expansion of these wind bubbles. So basically this is again not showing a simulation without magnetic fields. We find that the stars become hot enough. We use the Vink et al. Model. This was first adapted to Orion by Stellar Offner, and then I updated it in a previous paper to use this Vink stellar modeling and the same way that he treats the wind velocities. And what you find is that the winds start to go off and the star reaches about 20 solar masses. At this point, the stars are still contracting down to the main sequence, so they're still bloated. So the winds will be kind of weaker than if a 20 solar mass star on the main sequence. And so basically the winds start to shock heat this material. So I'm showing the density, the temperature, and the velocity magnitude. Because remember, the idea is that the winds will shock heat the infalling material, and you'll develop this really hot, low density, fast gas, which is what we're seeing here. And what's interesting too is that you see this pinching, and this pinching is due to the fact that you build an accretion disk around the star. And so just like radiation pressure, similar to outflows too, you basically get this flashlight effect. So basically feedback is not, all these forms of feedback are not acting isotropically, even though, for example, stellar winds and radiation pressure is isotropic. Radiation and winds given off the star is spherical. So basically the high density material that surrounds the star is causing feedback to be less effective. And so basically once the winds become powerful enough, so this wind started about 21 solar masses, once the winds become powerful enough and you develop these wind driven, we usually call them bubbles, but in the context of massive star formation itself, they're more like these lobes. You cause the accretion rate to actually drop a lot. But now we can also look at what happens when the core material is magnetized. And we see a similar effect to what I was saying before about how magnetic tension actually inhibits the growth of these low density bubbles that are shaped by feedback. And so you can see here, so again, looking at the density, temperature, and velocity magnitude, at these scales, we see eventually we do generate a much smaller hot gas bubble that's generated by stellar wind feedback, but it's not as efficient when we don't have magnetic fields. And then if we look at the accretion rate, you actually find that the accretion rate increases and then eventually decreases. And so the question is, well, why is that actually happening? Because usually when we think about feedback, we think that it's actually going to be more effective at shutting off the accretion rate, not increasing it. Well, again, it's similar to what I've been saying before about this magnetic tension. So here I'm showing the magnetic pressure divided by the thermal pressure of the gas. So early on, you see the magnetic pressure is much, much greater. And then eventually, once wind feedback becomes strong enough, so you can actually generate this hot gas and have the hot gas pressure be stronger than magnetic pressure, and that will allow for the expansion of these wind bubbles. And so here, for example, I'm showing this is the mass loss rates as a function of stellar mass in our simulations, the wind velocity, and the radius, the protostellar radius. And so you can see, so with the Vink et al. Model, this jump here corresponds to this jump at the hot side, or this bistability jump where the opacity changes. And that depends on the surface temperature of the star, which in turn depends on the radius. So that's why these two look different as a function of stellar mass, because the radius, which depends on the accretion history of the stars themselves, are not going to be exactly the same at the same stellar mass. Likewise, when you have this drop in the accretion rate, you have this increase in a factor of 2 in the velocity. And I didn't really include this here, but there's nice work. I summarize it in a previous paper where we looked at wind feedback from massive stars and intermediate mass stars, is that the production of these wind bubbles, or the fact for the gas to effectively shock heat and generate this really hot gas really depends mostly on the wind velocities. And so this is known as the fast winds versus slow winds. And it's really just a competition between, can you expand faster than you can cool? And so there's a nice paper by Chris McKee is one of the I apologize, I forget the first name, but it's a paper from like 1998, Q and McKee, where they looked exactly at this. And so this has really important implications for winds from different stars and how effective feedback is. But basically what I think is happening here is that, because these stars are still contracting the main sequence, when the velocities are pretty low, you're not getting the sufficient shock heating, or if you are, it's not expanding fast enough and you're cooling faster than it can do work on the surrounding gas. But then once the winds become fast enough, then you transition to this, instead of momentum driven, you're transitioning to this kinetic energy driven wind feedback. And that's what's shutting off the accretion flow. Likewise, we can also look at the comparison between where the wind gas is compared to the outflow, the entering outflow material. And I'm going to give you a fair warning that this is just looking at, this is just a projection of cells that have, of the density of cells that have some wind and outflow material. So this is actually over projecting the size scales of these hot bubbles. But what you can see here, if you just compare the entrained wind bubbles to the entrained outflows, you see that they are basically aligned. And this is suggesting that the winds themselves are finding the path of least resistance. And so that's why instead of getting what we expect, these spherical wind bubbles around massive stars, we're actually just getting these bipolar lobes. And so this is something that should be looked for. And just to, okay, so that was kind of like a full-on theoretical viewpoint of that. I'll just try to go through this a little quickly, but I just wanted to highlight some really nice work about, well, how can observations help us? And so this is some really nice work done by Grace Oliver, who is now applying for postdoc. So keep your eyes out if she applies to Carnegie, which I'm guessing she will. But she did this really nice study looking at using multi-wavelength data to look at the different feedback components in compact H2 regions. So these are small, less than 0.5 parsec H2 regions that are powered by individual massive stars. And so she looked at the direct radiation pressure by getting the bolometric luminosity for the stars. By looking at the infrared data, she looked at the dust reprocessed radiation pressure in these H2 regions. Likewise, from the radio, the free emission in radio, she was able to infer the warm photoionized gas pressure. And then likewise, using Chandra, she was able to find the shock heated stellar winds, infer that. So this is similar to a lot of the work done by Laura Lopez, who has done this for a larger sample of giant giant H2 regions in the SMC and LMC. So this was basically taking a lot of Laura's analysis down to much smaller scales. And so what Grace found was that for these compact H2 regions, you actually, you're dominated by the dust for process radiation pressure. And so this is important implications about what feedback mechanisms really are important when you are trying to model this. Likewise, the radiative force, like I mentioned before, depends on the stellar radiation plus the trapping factor. And so Grace was able to estimate that. And so basically she finds a median value of like 8 of 7 or 8. And that kind of says that the radiation pressure in these star forming regions around massive stars is actually enhanced by a factor of a few. So that's very important to say that radiation pressure and massive star formation is enhanced by a lot. And then one question we plan on looking at is, are these non-X-ray detections or source confusion, is it due to early confinement of stellar wind feedback? So most of the X-ray observations that she has are upper limit. It's hard to disentangle the X-rays, the hot X-rays, like let's say a few keV X-rays from the star itself, because we know that from previous studies that O and B stars do give off high energy X-rays, or is it just that because, like I showed before in the simulations, these bubbles are confined, and that will reduce the expansion and therefore lead to hotter gas that you would see in higher energy X-ray emission. Okay, and just the last few minutes, I'll talk a little bit how Grace also extended this, compared to her work to the previous work of Laura, to see what is the evolution of feedback in H2 regions. So this is just showing an example. This is from Laura's 2011 paper doing this nice multi-wavelength approach to studying the different feedback components in 30 Doradus. And what she found is that as of now, the dense shell of 30 Doradus is likely being accelerated by or controlled by the warm gas pressure from photoionized gas. But in the past, it was likely PIR and P direct dominated. And these X-rays themselves are actually the hot gas generated by wind feedback is much weaker than we actually expect. And so the X-rays are leaking out somehow, or the hot gas is leaking out somehow, which is why we see this very weak X-ray emission. So Laura also extended this analysis to a bunch of star clusters in the SMC and the LMC. So in the concept of these star clusters, they tend to be warm gas dominated, in contrast to what Grace had found. And the nice thing too is then by comparing Grace's work with Laura's work, you find this transition where basically the H2 regions around individual stars are radiation pressure dominated. And then once they expand to a large enough radii, they actually become warm gas pressure dominated. And again, the X-rays aren't that important. And some previous work I did several years ago, we find that there's a variety of ways you can actually lose energy from the shock heated gas produced by X-rays in star clusters. But the nice thing is that you do see this evolution of the importance of feedback from the individual compact H2 regions to the H2 regions that encompass star clusters themselves. So like I mentioned before, the importance of wind feedback is still kind of like a hotly debated topic. So, I find in my massive star formation simulations, wind feedback may actually shut off the accretion flow eventually. That will of course depend on how mass is delivered from the stars. So one thing that we're going to look at with StarForge is to kind of see how does feedback and the infall of material actually affect the formation history of massive stars. So I was limited by that in my previous simulations. But in the context of the star clusters, we find that the hot gas in these H2 regions, the emission is much weaker than we expect. So if you were to compare the energy density in the hot gas to the energy density injected by winds, what you find is that it's much less. So somehow this wind energy is being lost on these larger size scales. So some previous work, so in my 2014 paper, we talked about a bunch of different ways you can lose the energy. One of the ways that we talked about was turbulent conduction, where you can actually mix the cold and the hot gas on small scales, and that can lead to like a rapid energy loss. So Lachlan Lancaster at Princeton, he came out with a couple of these really nice papers showing like what happens when you have a stellar wind bubble from a massive star, or when you have a stellar wind injection from a star cluster into a turbulent cloud. And he finds that you actually get this efficient cooling due to turbulent mixing at the interface, and you can lose a lot of energy that way, because the shock heated gas will be really hot, 10 to the 7 Kelvin. But then if you cool it, if you add enough mix it with cold gas, then you end up getting 10 to the 4, 10 to the 5 Kelvin gas that then will rapidly cool. It's at the peak of the cooling curve. And so then you basically, instead of the H2 region shells being driven by energy transfer or being energy driven from wind feedback, it actually tends to be momentum driven feedback, because what happens is you radiate away all the kinetic energy. And so that causes wind feedback to be a lot less effective. And so some previous work by Monica Gallegos Garcia, she was a Banneker intern at Harvard several years ago, and now is a grad student at Northwestern. So she actually looked at this in more detail to see like how you can drive these wind bubbles. So this is a star cluster of a bunch of B stars, and what she finds is that as the bubbles expand, you have the overlapping wind bubbles that then mix at the interfaces, and you get a lot of turbulent mixing even within the bubble, and you can actually generate turbulence, so Kolmogorov turbulence. It's subsonic because the gas is so hot but so fast that's effectively subsonic. And so the nice thing too is that you do get this, you drive the subsonic turbulence within the star clusters, and that can also lead to radiative cooling as you're mixing in gas due to instabilities at these bubble shells. Okay, so just to summarize, oh, good timing. So I, talked a lot about how do these different feedback components or feedback processes affect accretion onto massive stars. The first thing I discussed was that the radiation pressure barrier is no longer a barrier in massive star formation as long as you have an anisotropic accretion flow, which you get naturally from the fact that in falling gas has angular momentum, you develop an accretion disk around the star. Likewise, outflows, which are launched during the accretion process. Outflows are really important for setting the star formation efficiency of the massive cores that these stars are expected to form out of, and also our simulations agree with the intrain outflow energetics that have been observed. And then finally, too, once stellar winds become important, so once you get into the fast wind regime, where your winds are fast enough to really generate this hot gas, that may potentially shut off accretion. And so, at least in the non-magnetic case, I ran it long enough so that you see the accretion rate drops a lot. But my opinion too is that, like I mentioned at the beginning, massive star formation is a highly dynamical process. And so the importance of feedback is going to really depend on the ram pressure of the material that's falling in. And so that's something that we will look at next. The dynamics of compact H2 regions that surround individual massive stars tend to be dust or radiation pressure dominated. And then once these H2 regions expand to encompass the whole star cluster, then they switch over to being warm gas, photoionized warm gas dominated. And then finally, one way that you can make stellar wind feedback in star clusters less affected is by this turbulent mixing that then can lead to efficient cooling. So I'll leave it out there. Thank you.
All right, thanks a lot, Anna. So if people have questions, go ahead and raise your hand, and then I can call on people. It looks like Mike is first. Go ahead, Mike.
Hi, Anna. Thank you for a fantastic talk. So it was really nice to have you share your work on stellar wind dynamics because we actually just had Lancaster last Friday. Talk about this picture. So just sort of trying to understand how your findings and his sort of connect to each other. His finding was that you get this sort of efficient cooling and the wind behaves as a sort of momentum dominated wind with a, T to the 1/2 expansion law. Now that was on GMC scales. Does that picture also apply on core scales according to what you're finding, or have you looked at this?
I'm actually been meaning to look on that. That's the next thing on my list because I want to look at the levels. So just to kind of go back here. So like I said, it's still a work in progress, but I think these results are cool. So yeah, Lachlan stuff depends on the, it's parameterized by like the total energy injected in this and that. What I suspect is we do see this, and I think, this is the challenging part, right? Because those are basically, when you think of the analytical models with a specific radius and that, it's highly oversimplified where you're just, it's, an isotropic bubble that's expanding. And I think the problem is here is that it's actually a lot of, it's much more complicated than that. So it's hard for me to think about, like, I do plan on, the next thing I plan on looking at this is what is the effective bubble size. What I do find actually in my previous paper that I think is contradicts what Lachlan was finding is, so I did this previous paper, with Stella and Laura Lopez and Mike Foley, where we looked at the formation of wind bubbles around B stars, so focusing on high mass B stars, up to 13 solar masses, and low mass B stars. And I did compare the bubble radii with the analytical expected bubble radii from Weaver et al. And I do find that they do agree. So I think I have a feeling is,
I didn't get that.
Sorry, I don't know why she keeps going off. I think that it's an energetic phenomenon. Like, it's going to highly depend on the energy that gives you an effective, velocity in a way. And that will increase the development of the instabilities, because a lot of these instabilities that you expect to happen with like turbulent conduction or turbulent mixing depends on, you know, the formation of Kelvin-Helmholtz instabilities, which, as you know, happens, you know, between two shearing flows of different velocities, and it's enhanced based on the velocity difference. So I think in the context of individual stars, I don't, just based on that argument, I don't expect to be as efficient as what Lachlan is seeing with his star cluster simulations. And another thing too is his simulations are still, you know, it's kind of treating like a star cluster as a point source. And that can also, and so you give it one very large kinetic energy. And I think it's more complicated than that. And I mean, you and I have discussed this, where we definitely plan on looking at this in more detail with Starforge, which I think is the way to go.
Cool, thank you.
Ilva, go ahead.
Thank you very much, Anna, for such a nice talk. I was curious, what's the maximum mass that your stars can be created here, and what's your take on how you create those very most massive stars of like more than 100, 200, 300 solar masses?
Yeah, so the most massive star I've made so far is the first simulation I showed, just radiation pressure, and that was like over 60 solar masses, which was the biggest at the time. However, of course, as I added more complexities, so outflows, like I showed, the accretion rate drops because well, it's not so much the accretion rate's dropping, it's that you're losing mass into the outflow. And so those stars become less massive by the end, or by the time I start running them. One of the biggest problems with simulations like these is that as time goes on, it gets a lot more complicated, you know, and so it takes a lot longer to run. So it comes to a point where I need to, you know, move on with my life and write up the paper. I will say though, we do plan on, sorry, Mike's gonna love this because I keep like, all this work is based on, isolated massive cores. And as I discussed before, and Mike's writing up now, is that it's not quite a simple process like that. You actually, and what the observations have really pointed out is you have these large dynamical mass flows. And I suspect that in places like the Doradus, that either because those star forming regions are so dense, and this is what I plan on working on next with Starforge, similar to what Mike and David is working on, but with much denser initial conditions, is to really look at the sites of where massive stars are forming, and also to kind of look at the mass flow compared to the combined pressure from the different components of feedback. And so, at least in the simulations here, it seems like stellar winds are limiting the stellar masses at the end. But what I expect is that it's going to be highly dependent on how you can deliver mass to the stars themselves. And so I think that will have us be important for us to kind of understand, like, where do the most massive stars form? Because I know there's work by like Selma and others, like could the most massive stars form by stellar mergers and all that. So we definitely plan on looking at that to see how does the formation of the most massive stars depend on environment, and then also different feedback components. And that requires not what I have done so far, that requires Starforge, where we can resolve individual stars on GMC scales and really follow that the mass flow.
Okay, yeah, thank you. And may I ask a second question, Kai?
Yeah, go ahead.
Okay, thanks. So can you somehow include binary formation here, or is it all dependent on that you start with the core of the star already?
We do get fragmentation. So at least show this here. I didn't talk too much about it, but like for example, in these runs, and the same thing happens. Actually, I get more fragmentation when I have outflows because you have less radiative cooling. You have more time for the densities to be enhanced and to collapse. So in this paper, or not this paper, but in the next paper where we include outflows, we do see more of an increase in the turbulent fragmentation. And that tends to form wider binaries, whereas you get these close-in binaries, you get disfragmentation, but the disk has to be sufficiently massive and large enough to fragment. And that can be dependent on resolution, of course. Also how, in the case of magnetic fields, how angular momentum is removed. So that's something I definitely plan on to look with, like in running non-ideal MHD simulations where we can track the formation of accretion disks better and be more realistic. And then one of the major problems we have in this is when to decide if stars merge, right? So like in these simulations, the best resolution I have is 20 AU. We have to assign a sync radius. So we assign, any, material within 4 cells will be accreted onto the star. So it's hard for us to really decide, okay, if a star comes in 20 AU, 20 or 80 AU to the star, do we know if it accretes or not? So that's, if they merge. So that's something that I think we'll definitely be thinking more about how to model that better.
Yeah, interesting. Thank you.
Yeah, you're welcome.
All right, maybe time for one more quick question if anyone has one. I don't see any other hands raised. So if you have other follow-up questions, you can feel free to email Anna. Otherwise, thanks again for joining, and thanks, Anna, for the very nice talk. Thank
you. Thanks for having me. Enjoy the sunny California weather. Starting to get cold here. Winter is coming. Bye, guys.
Thank you.
Thank you.
Thank you.